Foundation has been organizing. So this is just one of the kind of events, and there are multiple events going on through this foundation. So my first, I am Arun Kumar Avasthi, and today's expert will be Dr. Sunil Chandra. I will introduce us in a bit of time, but first let me introduce this foundation and what it is about and what are its. First of all, let me request everybody to mute their microphones as soon as they are joining. कृपया अपना माइक्रोफोन जिस भी डिवाइस से आप ज्वाइन कर रहे हैं बंद कर दीजिए, वीडियो भी, क्योंकि मोस्ट ऑफ द टाइम हम यूजुअली इंटरव्यूअर और एक्सपर्ट ही वीडियो में होंगे। और मेरी रिक्वेस्ट है ज्वाइन करने वालों से दैट व्हेन दे लाइक टू आस्क क्वेश्चन, द पॉडकास्ट इवेंट इज लाइक दैट ओनली। इस तरह की इवेंट्स में one can interfere at any time. So if you feel like asking a question based on our discussion, so the format of this podcast is we will be discussing about a topic. So if you feel like asking a question, you can put it in the chat box, and then we will I will put the question to the expert as and when it is found relevant. Okay, so let me first start with the introduction. So the foundation under the banner of which this particular event is being organized is called United Science Foundation. Since I have been in the group since long time, let me tell you, that before this United Science Foundation, this was also known as United Science Forum for a while. So if you go on Google to search this kind of foundation, in addition to United Science Foundation, if you find something attached with the name of United Science Forums, this is also kind of activity organized by this group. And today's expert, Dr. Sunil Chandra, is also the president and the creator of this foundation. Thankfully, I think a few 1 month back or so, our foundation got registered as a national non-profit organization, and the role of this organization only is to enhance the visibility of science in general knowledge and science as a career among the students who are less privileged in terms of getting these knowledges online or through experts. So ये यूनाइटेड साइंस फाउंडेशन, इसका मेन उद्देश्य सिर्फ यही है कि हम जो भी ज्ञान हमने एज एन एक्सपर्ट अभी तक अर्जित किया है, सो ये ग्रुप ये नॉलेज आने वाली नेक्स्ट न्यू कमिंग जनरेशन को ट्रांसफर करना चाहता है. सो ये नॉन प्रॉफिट ऑर्गेनाइजेशन, इसको स्टैब्लिश हुए मोर देन 1 ईयर हो चुका है, एंड जो डॉक्टर सुनील चंद्रा हैं वो इसके फाउंडर भी हैं और आज के एक्सपर्ट हैं. सो मूविंग फॉरवर्ड, मैंने थोड़ा बहुत इसके बारे में ऑलरेडी इंट्रोड्यूस कर दिया है. सो आई विल जस्ट इटरेट द बेसिक मोटिव्स बिहाइंड दिस. The motivation is the social cause, that is strengthening the science awareness and rational thinking of the citizens whom we can reach, especially the next generation. And from time to time, like this is also a part of event where we can, with our best of capability, do student counseling, especially in the rural areas. So as I have already told, United Science Foundation has taken shape in June 2019, and now it's closing to be 2 years old. So congratulations to all of the members of that, and hopefully we will be able to present some of the things. So here is how you can find the United Science Foundation on the social media. So it's like from the website, where, as I told, this is this was United Science Forum in the beginning, and this is a Gmail. It's an official Gmail we are using, and Apart from that, the Telegram is also available. We are available on Telegram, YouTube, Facebook, Twitter, WhatsApp, and Instagram. So mostly the social media which is now being used by users have been covered. So most welcome to come in this. And there are different kind of membership. So I will not get you bored with this, but I would just like to tell that there are about 100 members already in this foundation, and there are different kind of members. So I mean, it's like a tree hierarchy where there are main board, life members, student members, school college representatives, and associate members. But I would like to just mention here from this plot that we have members from all over India. So that's a very, in fact, we have members from international community as well. So it's a great pleasure to introduce this. यूनाइटेड साइंस फाउंडेशन की पहली रूरल सेक्टर में जो इवेंट हुई थी वो अजमलपुर साइंस मेला के नाम से 2019 में हुई थी, और ये उसके कुछ स्नैपशॉट्स हैं, और ये लेटर ऑन पेपर्स में भी अच्छी तरीके से कवरेज हुई थी, just to give outreach to the persons who could not reach at that time. Of course, this was the last when we could meet in person, because COVID had taken over afterwards. So इस तरीके की मीटिंग फ्यूचर में प्लान होंगी, बट बिफोर दैट आई थिंक टू गेट एवरीबडी engaged एंड टू प्रोसीड, हम इस तरीके की ऑनलाइन बहुत सारी एक्टिविटीज भी करते हैं. सो उन एक्टिविटीज में डिफरेंट काइंड ऑफ एक्टिविटीज यूएसएफ करता है, जिसमें कोविड-19 अवेयरनेस है प्रोग्राम, जिसमें हम वॉलंटियर्स के थ्रू सोशल मैसेजिंग और डिफरेंट जो इम्पोर्टेंट मैसेजिंग है वो सोशल हैंडल्स पे शेयर करते हैं. इसके अलावा हम लोग साइंस न्यूज हाइलाइट्स भी अपने ब्लॉग्स पे और वेबसाइट पे पुट करते हैं, मेनली शेयर्ड बाय डॉक्टर पंकज कुशवाहा. And last but not the least, and more are adding, but in this is USF podcast event, which we call Ask Us. So the main motive of this podcast event is, while we are online discussing, आप लोग questions put up कर सकते हैं, and it is my duty to interrupt the expert and get your questions answered. So feel free to ask questions. So we were already on this page where I was telling that this is the 4th episode of Ask Us event, and the title of today's Ask Us event is Black Holes. Since the expert Dr. Sunil Chandra is an astrophysicist who has done a lot extensively on black holes, so we would be covering a few of the questions which are put here in the poster, and lot more, and also the questions coming from you. So let me first introduce the expert here, who is Dr. Sunil Chandra, and after doing his BSc and MSc from University of Allahabad, he did his PhD from Physical Research Laboratory, Ahmedabad, and later on post PhD employment as a known as postdoctoral researcher. He did first in Physical Research Laboratory, then moved to renowned Tata Institute of Fundamental Research in Mumbai, and then from there he moved on to Center for Space Research, Northwest University, South Africa, where he is at present a postdoctoral researcher, and he is joining from there itself. And it's not very difficult to introduce me, the host of this session, because I share the education as well as up from BSc up to PhD, similar to what Dr. Sunil Chandra has been through. I have also done my BSc MSc from University of Allahabad and did my PhD as his PhD batchmate in Physical Research Laboratory. Of course, our area of expertise were mainly astronomy, but he is working on black holes and stars like stuff, and I'm working on the nearest star, that is the sun. So maybe in some future, maybe I will also introduce about the sun in this kind of Ask Us event, but today let's focus on the expertise details on black holes and why we have. Okay, so before moving forward, the moderators of this session are Deepti and Ritika, and they will be taking care of questioning questions and interrupting me if I do not catch the questions. So the motivation of this organizing the Ask Us event today about black holes is the discovery. So the discovery, Dr. Chandra will give more detail about the discovery, but let me just put 2 slides on it. The discovery was by making a smart Earth-sized virtual telescope, and this is done by linking the telescope, which was across the globe in 4 continents. Scientists have made directly imaging a black hole. हिंदी में कृष्ण विवर कहते हैं. तो 4 कॉन्टिनेंट के टेलीस्कोप का डेटा लेकर, जिसको एक कहा जा सकता है कि अर्थ साइज का वर्चुअल टेलीस्कोप बना के साइंटिस्ट ने इस तरीके की ब्लैक होल की इमेज की संरचना की थी. तो ये अपने आप में ये डिस्कवरी है, क्योंकि पहली बार साइंटिस्ट रिसर्च कम्युनिटी ये कर पाई या देख पाई. इससे पहले सिर्फ मॉडल्स में और स्कीमेटिक्स में ब्लैक होल्स की पिक्चर हुआ करती थी. एंड फर्दर डिस्कवरी जिसमें डॉक्टर चंद्रा डायरेक्टली इन्वॉल्व है, दिस इज द डिस्कवरी ऑफ मैग्नेटिक फील्ड इन द ब्लैक होल्स पेरिफेरी. सो यहाँ पे जो पिक्चर मैं शो कर रहा हूँ, यहाँ पे जो आप स्ट्रीक्ड लाइंस देख रहे हैं, these are actually the lines representing the magnetic field around the black hole region. So with this introduction of today's Ask Us event, let me invite Dr. Sunil Chandra to take us to the journey first about the black holes. So welcome Dr. Chandra in this again event. So I hope Deepti, I hope now it is getting recorded.
Yes, it is getting recorded.
Yeah. Okay, perfect. So welcome Dr. Chandra. My first question, and consider also me as a naive. So what is a black hole, and is black hole a star?
Okay, thanks Arun for nice introduction of our organization and about me, my education, etc. Hyping it a bit. But one thing I would request before we go ahead, can we make it more like one-to-one discussions by switching off the sharing?
Yeah, sure. Presentation. Yes. Okay.
Also, you okay? Good. Thank you. And also one request, I mean, same time as you said, I am also co-host, so I'm also getting emails, and so I would request Deepti to take care of email. Somebody has requested for link. Can you just forward that link? Doesn't matter who is that.
Yeah.
Okay.
Yeah, sure. Yeah.
Okay. So welcome you all that you are part of this event where you will listen me. And basically the mode of Ask Us is like, we try to avoid the PPT or whiteboard or blackboard writings. What we try, we converse, we talk each other and talk to our invitees or attendees. So we talk formally, informally, and talk about the stories. So basically, if you are, I mean, since you asked, like, what are these black holes? So actually, there are 2 ways one can understand black holes. One is like theoretically. If you go theoretically, black holes are nothing but a theoretical singularity. I mean, it's like, it is said that it's a puncture in a fabric of cosmos. And concept of fabric of cosmos comes from the theory of general relativity, which says that this cosmos is, I mean, everywhere you can find this is space and time. This is the fabric of cosmos by which it is defined. And any gravitating object will bend this fabric depending upon its mass and density. And depending upon its mass and density, it will make a depression in the fabric. And theoretically, actually, black holes are an object which is concentrating nearly infinite mass in a nearly zero size. So this means mass is enormous and size is very small. So you have kind of a puncture in your um, what we call fabric of cosmos, or space-time fabric. And basically, if I want to emphasize two exotic things, so I will not talk about GTR approach of defining black hole or theoretical perspective, because for many of our attendees it will be a very boring thing, because they are
I,
graduate postgraduate
I will come,
students.
but anyway, I will come to it later on, not now.
Okay, good. So
बट
actually,
लेट मी ऑल्सो इंटरप्ट हियर, जैसा कि आपने
mhm.
कहा कि जो ब्लैक होल है, दे आर लाइक पंक्चर इन ए फैब्रिक. दैट्स अ वंडरफुल एनालॉजी. सो एक कपड़े में इट्स लाइक आपने कपड़े के सेंटर पे एक बहुत ही भारी ऑब्जेक्ट रख दिया है.
करेक्ट. हाँ.
तो बिफोर, जैसा कि मैंने अभी बताया कि बिफोर दिस डिस्कवरी, जब हमने अब ब्लैक होल वाकई एक तरीके से ये कह सकते हैं कि ऑब्जर्वेशनली डायरेक्ट इमेज फोटो खींची एक तरीके से, तो इससे पहले ये तो 2019-20 की बात हो गई, बट ब्लैक होल की डिस्कवरी तो बहुत पुरानी है. सो हाउ डिड यू नो कि इस फैब्रिक के बीच में देयर इज अ वेरी मैसिव ऑब्जेक्ट एंड which you call a singularity?
Okay, if I am an observational expert, so then I would say that we cannot see black holes, because what happens whenever we have, I mean, I want to go in this way, like when you have, like earth is having gravity. So when you want to throw some pebble out of the earth's gravitational field, you have to have some velocity called, you start with the velocity called escape velocity. Same way, just imagine, I mean, somebody had imagined it in 1800 or something, that there may be some objects which are so heavy that their own gravity can not let even photons go out of its effect. So it's called dark object. So basically that came long before that idea. And after that, when Schwarzschild solved this equation of general theory of relativity by Einstein, and he got that there will be something more massive in a very small sized, I mean, black hole term came afterward. John Wheeler coined this term during one conference, and it became hit. Actually, it is called a black hole because even its gravitational field is so strong, even light cannot come out of its effect. I mean, it's bent so heavily that it's just going within that system. So how we see that? We see its effect on the neighborhood. Whenever there is a black hole, it is having so strong gravitational field, so it will have effects in surrounding, so in the surrounding matter. तो जो आसपास का मैटर है उस पे जो इफेक्ट होता है, अगर हम उसकी स्टडी किए तो करें तो हमें पता चलेगा. Actually, very first observational indirect evidence was this Cygnus X1. In Cygnus X1 was observed by X-ray satellite, and what we saw that this very hot gas is swirling around some very tiny region of space. And if you use very simple mechanics, use like a gravitating body and a mass is moving around, and use very simple equation, and you will see that the mass required for having that kind of kinetics will be so massive, very massive.
It has to be very massive to hold a galaxy, spiraling around.
That is different breed of black holes. I mean, black holes I mean, this is one picture how we started observing.
Okay.
In fact, observational investigations started soon after the its proposal. Like there may be some exotic kind of objects lying in our universe which we don't know. Let us find. I mean, these are fine. Now discoveries have revealed that even each and every galaxy is hosting a breed of black hole. I mean, breed means that supermassive breed, not
Right.
a smaller time as size scales. They are super massive black holes sitting at the centers of each and every galaxy. So black holes are not rare. Earlier it was like it may be rare, but black holes are not rare because each and every galaxy is having. But it is still rare in a sense. If you take mass of entire universe and mass of all those black holes, is still mass of black holes are really a very tiny in that comparison, total mass contribution to the universe. Okay,
I
so
see.
this,
तो इसका मतलब कि जो मतलब आप जो ब्लैक होल पहले थियरीज में और ऑब्जर्वेशन में आपने देखा कि जो ऑब्जेक्ट हैं जो ब्लैक होल के सराउंड में हैं, दे वर होल्ड सो टाइट कि उनको बांधने के लिए एक बहुत मैसिव ऑब्जेक्ट जो है चाहिए था। तो एक क्वेश्चन इससे रिलेवेंट एक क्वेश्चन अभी मोहम्मद हमजा ने पुट किया है, थैंक्स फॉर आस्किंग क्वेश्चन राइट अवे, कि सर हाउ कम ब्लैक होल्स sorry how come black hole eats a whole star? Can so okay, so my question when the black hole comes, you are going to get a lot of questions. So my question is, first, is black hole a star?
okay, no, black hole is not a star. A star is a term coined for some particular kind of objects which are actually burning hydrogen or helium or some lighter element to make heavier elements. So there is some kind of energy generation process at the core, and you are getting emission out of that. It's another system, like our sun is our star. Sun is our star. Basically, for many studies, we use the physics what we understand using sun or solar observations. We apply that as a template to understanding other phenomena on other kind of objects. So no, black holes are not stars. They are stars are different, but yes, black holes are formed when a heavier star dies. And like every thing we know, if something is created, it will die. So like us, even stars are not immortal, they are mortal, they will die. So star like sun will also die. And how and I will come to the point, like how they will die, because stars are alive because they are generating energy. They are throwing that energy out and they are sustaining its size. मतलब उनकी एनर्जी जनरेशन प्रोसेस की वजह से ही उनका साइज है, क्योंकि रेडिएशन is generated in the core and it's holding collapse. Collapse means even, more massive star will be more unstable. That is different story. Life cycle of a star will depend upon its mass, okay, and chemical composition. But at the end, star has to die, because if you stop the energy generation at the core, what will happen? There will not be any force to stop the compression, so it will compress. And at the end, this compression may, depending upon its mass, it may end to violate first force. Just I will go for the students. When you start compressing, there is nothing producing energy at the core. Then what will happen? What is next force which will stop compression? Huygens uncertainty principle, that will try to stop this compression. It's called electron degeneracy pressure. Okay. And then if your compression, I mean the force which is compressing is not enough to overcome, then that star will stop compressing. That electron degeneracy pressure will hold that. And this happens in the case of white dwarfs. Okay. But suppose in cases where you have this compression, I mean initial mass is so much that this compression is overcoming that force, and then there is next level of uh, force. I mean this force is in nature those short range nuclear forces. They will start opposing at nucleons level. Okay, because no two, just like electrons, no two nucleons can have all the four quantum numbers same. So you will have another force, nuclear force, which will stop and try to stop. But if that is the case when you have everything is made up of nucleons like neutrons, so that is the case when you have neutron star. Okay. And another stage, if your compression force of compression is so high that it can come to overcome the nuclear force, then there is no natural force which can stop compression. And this is why black holes are called as a infinitesimal size, I mean nearly zero size, because we don't know, there is no force which can stop compression.
Yeah,
So
they keep on getting compressed and compressed
yeah,
to a
yes.
theoretically zero size.
And I yes, and you know this
So I think
small
this,
g.
sorry, yeah, this answers the question of Muhammad who put it, that black hole actually is not eating a star. It's the corpse of a star. So when the star dies, the black
Yes,
hole
yes.
forms, and
Okay.
not every star's death forms a black hole, right?
Yeah,
So
it may.
we'll come to that later. Actually, there are, I think, a lot of questions. Before even I put questions, there are a lot of questions. So let me put another question so that we can move forward. Sorry. So if a light beam, this question is put up by, okay, the name is arbitrary. So if a light beam is directed towards the singularity of black hole from outside of the black hole after crossing the event horizon, will the speed of light increase beyond the speed of light by the immense gravitational force created by singularity, as it seems so? So it
Okay.
what I got from this question is, yeah, that means it's another paradox. So if the maximum speed of which goes out of a photon which goes beyond the event horizon close to the black hole, can the black hole increase the speed of light?
Actually, I may not be very right person to comment on this, because it's a mostly a theoretical perspective
Theoretical
on that.
concept, yes, yeah.
Yeah, but one thing is that if when you are very close to singularity, even the laws of GTR doesn't hold. So mostly we don't know the nature of
Yeah, we cannot predict,
fields.
and there it's maybe not very right to say that speed of light is the maximum speed. Maybe I'm wrong, just
No, I
yeah.
mean the laws of nature. What we know is governed by special theory of relativity or general theory of relativity.
Yeah.
They hold in a normal, I mean even close to event horizon also you can have pretty good prediction by GTR even after event horizon, but close to singularity, no. I think things violate,
Yes,
GTR
yeah,
violates. So
yes,
I cannot comment about whether photon will have higher velocity or lower velocity, but one thing is sure for certain. When you are very close to singularity, you are not sure about the photon itself, whether
yes, yeah,
it remains the information of a photon. Another thing is, like, I want to just comment others who are not aware of studying black holes and all. So one comment is like, black holes are very simple objects if you want to understand them, because they have one parameter called mass, You should know mass of those. And second thing is like, it should have, I mean, you should know their spin. Why they have spin? Because mostly the black holes are formed by either death of a single star, and each and every star is kind of having angular momentum in spin angular momentum. So in order to preserve those angular momentum, that it's a very natural to know that अगर शुरुआत में रोटेशन था, तो मरने के बाद भी रोटेशन तो खत्म नहीं हो जाएगा ना. There will be rotation. So black holes will be having some kind of rotation, and that is angular momentum basically. So इसीलिए black hole will have spin. Second thing, many of the black holes, large ones like intermediate mass black holes or supermassive black holes, these are formed even small size scale.
So you mean to
They
say that
all are formed due to,
black
yeah,
holes
they are,
are characterized based on their masses also. So when you are saying high mass black holes, low mass black holes, so okay, so this leads me to my next question. But before I go to my next question, there is a related question by Mubashir. Sir, will you please throw some light on singularity first? What is singularity?
okay. Okay, singularity is basically a concept where you have kind of infinite gravitational mass, I mean infinite mass, putting to the infinitesimal size of the space. Like huge mass is concentrated on a very small, I mean nearly zero. So what will happen around that? If you see, the depression in fabric will be kind of a hole, okay, because the nature of gravity close to those will be very extreme. Why I'm telling you extreme? Because if you see the I mean this gravitational force equation, if you see it contains like small g, right? It contains a small g, and a small g contains the mass of that object and radius of
Small,
that object.
by small g you mean the gravitational one, and there is also a capital G which is used for gravitational constant.
No, capital G is a constant. I am telling the
Yeah,
gravitational
that's why you put
acceleration.
small g. Yeah,
Yeah.
so I yeah.
Acceleration, gravitational acceleration contains
Acceleration, yes.
terms. It is proportional to mass of that object and size of that object. Reversely proportional to size. Size का okay. Size का square है in fact. Then size अगर zero कर दो, तो small g is infinite. Then force will be infinite. So I mean एक layman के लिए
Yeah,
यही है.
there's a limit to everything, and इनको सबको explain करने के लिए we in theory you need to use the word tending to. We need to yeah yeah.
Okay. Yeah.
Yeah. Okay. Thanks for getting into this question in detail. And two of the questions from the audience are in the line of my next question. So the question from Rishabh Yadav and Satyam Yadav is actually my next question. How we derive the mass of these objects, since the experts are classifying the black holes based on the mass. Can we is it possible to derive the mass of the objects?
Yes, definitely, definitely, it is possible. And very first uh, effect is in the surrounding, right? I mean, I'm not telling that you are measuring I mean its effect close to that singularity. No. If there is a black hole, it will exert immense force on the matter in the surrounding. So if you study the matter in the surrounding, then you will see the effect of strong gravity. So basically, studying those effects, you predict what will be its mass and what will be its size. Basically, mass is size of a black hole is characterized by the size of event horizon. A fictitious, I mean a very imaginary kind of surface around a black hole from where light cannot come out. So
So
if light,
it's like a two-body problem. Like we assume that the sun is there and the earth is there, and we can see the we can observe earth. We can also know, let's say, the mass of earth, and we can also know the distance from something which is, for this two-body problem is sun, but for the problem of black hole is black. So from that distance, and so you mean to say this, that from that distance and the mass of the object which is revolving around, we kind of get the idea of mass of this.
yeah, I mean, in fact, there are many ways we measure
Mm-hmm.
masses, but
Mm-hmm.
mostly, I mean, just one example. So suppose there is a highly gravitating object like a neutron star or a black hole, and you have supply of gas towards it. Okay, then it will form I mean, the matter will fall because, you know, from high potential to low potential. Okay, matter will fall on this object, and it will attain more and more energy. I mean, I would say more and more, it will lose its angular momentum and potential energy to reach the object, right? So when that matter goes to closer and closer to the gravitating objects, it interacts with already existing matter, right? So it gets heated. Okay, so in this process, as you go closer, you have more force on those matter, and matter gets more heated. So in this way, you are having like a gravitating object, and in surrounding you have very hot gas swirling around. So what we do, we know that if gas is hot, it will radiate. So we study, I mean, we observe those using some telescopes like X-ray, ultraviolet, or optical telescopes. And what we know, that this gas is emitting and it's moving. So using those radiations and properties of those radiations, we can predict what will be the mass of that object. This is how. Uh, and in case of another example, our next neighborhood is like we are part of Milky Way, right? So in case in the center of Milky Way, there is a supermassive black hole. I mean, a black hole which has mass something like 10 to the power 6. I mean, roughly, I mean, it's a million, right? Million times so mass of the sun. So that
So
can be.
million suns make a black hole which holds this thing, which is closest,
Um,
right?
yeah, I mean, I am not telling that the mass of the black hole is holding entire Milky Way galaxy. This is not correct.
Sure.
Actually, black hole, if you are very far away, the effect of black hole will have same as you have something else of the same mass. Okay, it's the entire I mean, I should say composite mass of those systems hold together. That is another thing. But in the case of one study of those stars around Milky Way, people have studied like the 20 years. I mean, this year's Nobel Prize, 2020 Nobel Prize was given to that discovery. They started seeing the stars, motion of the stars, and when, I mean, when they are passing through one particular point in space in our Milky Way, it gets accelerated. Okay, each and every star. So when you trace motion of those stars around around the center of our galaxy, what we see, all the stars are really following a trajectory around some point. And when you study the motion of those stars, you can derive using very simple Kepler's equations. You can derive what will be the mass of the gravitating point. So this is how mass of the black hole at Milky Way is derived. That is
I see.
another indirect method
Yeah,
of determining mass of the black holes. Yes.
I see.
Yeah.
Okay.
Hope this clears
So
some.
yeah, definitely. So now there are a few questions which are close to my next point on this discussion, which is what kind of instruments, like for stars and sun, there are telescopes which has lenses and all. So what kind of instruments are being used to detect things not coming out, but in the surrounding of these black holes?
Okay. So basically, detector wise or instrument wise, I mean, see, point is like these systems are kind of observed indirectly, I would say. Even using the direct imaging, I would say indirectly, because nothing is coming out of those tiny regions. So whatever is coming out, it's coming out of from the region away from the event horizon. Like, मतलब एक जो रीजन है इवेंट होराइजन, उसके बाहर से ही जो आ रहा है वो आ रहा है, राइट? We are not getting anything from the region within.
Yes. Yeah.
So what we do, we use like in almost entire well, first very what we call sophisticated or well developed area of investigation is like using electromagnetic waves or electromagnetic radiation, which are produced from the vicinity of black holes. We study them. That is very first tool. Second tool, which is developed over the years, is like, suppose you throw a pebble in a pond, what will do? It will kind of generate ripples on the water surface, and those ripples will move forward, right? वो जो सर्कुलर पत्थर फेंकने पे सर्कुलर जैसा वो मूव करता है ना बाहर की तरफ. तो similar happens when one black hole merges with other black hole, or one neutron star is merging with another black hole or another neutron star. So means two highly gravitating objects are interacting and merging to each other, then you will have ripples. Ripples where? Ripples in fabric, I mean our space-time curve, and that ripple move outward. If some, and those ripples can have effect on our local surrounding. Exactly, that's what LIGO is based on. LIGO is like direct detection of effects of those ripples, ripples, and that is already observed. That is the
So this
discovery by.
LIGO is a this LIGO is an instrument. What kind of
Yeah,
instrument it is?
it is one instrument, like it's called laser interferometry, and I mean it is based on laser interferometry detectors. Like, you know, interference. You have Michelson interference. You might have seen Michelson interferometer. So a beam of light is passed through a beam splitter, and it sends one portion of the beam to one side, and another goes in the forward direction, and they come back because you have mirrors over there. They come back and they interact and they generate fringes. Okay, so what happens if you're somehow these two arms, size of these two arms changing, then you will have change in fringe pattern. And if you observe change in fringe pattern, then you know that this change had happened due to this change in size of those arms. Exactly, this is what LIGO is based on. They are high precision vacuum based experiments. I mean, it's like kilometers of, I mean, of the size, those arms, but they are, I mean, the mirrors, they are like very nicely suspended mirrors. So they can change, I mean, if we, this length, I mean, distance between two mirrors are changing, then you will change, see the change in fringe. This is new technique. I mean, it's like a new technique, means technique is very old, but new instrument to detect information about black holes, LIGO. But mostly we observe through electromagnetic spectrum, because that is the most advanced and old method of doing astronomy. And can have another thing. I mean, another advancement in the instrument area is like you can have electromagnetic detectors on different energy ranges, right? You can have X-ray telescopes, gamma ray telescopes, optical telescopes, and something called radio telescopes. And radio is the one which people are more familiar in their
Yeah,
daily life. I mean, we are
yeah.
kind of connected to connected by phone and TV and radio and all those. These communication are made using that band, right? So what I want to say that using sub-millimeter facilities on ground, I mean, coordinating among them, we have come up with something. It's not like Earth-sized telescope. You already mentioned. You are using different telescopes at different locations on the Earth, making an effective area, effective what we call aperture, effective area of the telescope of the diameter of Earth.
So it means the
And
pixels are spread around
yes,
the whole. If we consider in terms of a mobile camera, the pixels are spread around the Earth,
yes,
over the
exactly.
Earth, 4 continents, and then from
Yes.
those pixels you create the image of something which is far, far away. So okay.
Actually, I mean, you can say that for layman, and it's a really very nice phenomenon, but very tedious because all the telescopes should be synchronized to a
Oh yeah.
very high precision. Because I mean, one can go to details of EST website and all those papers, and there are many. I would say that
So by
people should
EHT, you mean the
Event
Event
Horizon
Horizon
Telescope
Telescope,
Consortium.
uh, which
Yes,
is, yeah, which is the one which discovered, which is the, I
yeah.
think, the sole reason for
And
discovering.
here
We'll
also,
we'll talk in detail about the discoveries in
okay.
just in coming. But I think there are a few questions which I think can be answered right now. If we go to one of my questions, can you take us to the journey of formation of a black hole until its death? Because some of the questions they also ask what happens
Okay.
later on. Yeah.
I mean, let me start with an assumption that stars are born, and stars are some entities which are burning hydrogen at the center and converting to helium. Okay. This process is called nuclear fusion. So hydrogen atoms at the center of some object is fusing and generating helium. In the same process, it produces a vast amount of energy. Okay. Okay, this part of this energy is released. Okay, so this is very basic process by which stars are having energy, its own energy, its own radiation. They we can see. So biggest analogy is sun. Our sun is a star which is in its middle age, I should say, and it's generating a lot of energy, and which is responsible for our life on earth. Okay, so this way stars are born and they are fusing hydrogen, and in the later stages, what happens when your hydrogen at the center is consumed, then you have helium at the center. Hydrogen is burning in the layer. I'm telling burning. See, remember, burning in normal sense, it's called like you have it's chemical process. But here, burning of hydrogen means not a chemical burning. It's like nuclear fusion. So helium is burning, then you have hydrogen in layers. Then if helium is exhausted, next element is formed. Okay, this way this process goes. It's like onion like structure. In core something else is burning, and lighter elements in the surrounding. So this is a normal life cycle of a star. In this beginning, it's hydrogen which is burning, very efficient process. In later stages, hydrogen is burning, slightly poorer process, I mean energy generation process. This way you have uh, this way the life of a star goes through a curve where it is burning hydrogen, burning helium, burning carbon, but at the end it will burn, it will come to the iron. And after that, at the center, you cannot fuse iron, because for that you need a huge amount of energy to start with. So if you want to fuse iron, it's not possible. So at one stage, burning at the center will stop. Okay, this means the energy which was kind of keeping the compression, holding material to not to compress, it will not hold, it will start compressing. So core will start compressing, and since you have other light elements like hydrogen burning in outward, so it will end as a like outer layer will be thrown out, and inner inner portion will start compressing. So when this compression, uh, I mean, it depends upon the initial mass and compressing core. Obviously, the compressing core, if it is very heavy, then I already mentioned it will either end as a white dwarf or neutron star or as a black hole. You might be you might have heard about one of the very great Indian scientists, Chandrasekhar Subramaniam. Chandra Chandrasekhar had given one limit, that the minimum mass, I mean, this is like maximum mass which white dwarf can sustain. And if you add more mass to that limit, I mean, then it will end as a neutron star. So in the same way, there is a limit like 2.6 or 2.4 solar mass. Beyond that, if a star is kind of collapsing itself, it will end as a black hole if its initial mass is more than
So
2.6.
this also answers one of the question of the participant, that the sun won't become a black hole, because
Definitely.
you need 2 or higher times mass for a star to become a black hole.
Okay,
Okay, please go on. Yeah.
but this brings us one confusion in the audience.
Yeah.
Confusion is like, this means in principle we cannot have a black hole which is having mass lower than 2.6, right? No, black hole can have mass. I mean, theoretically, black hole can have any mass, I mean, very minuscule to very huge, but there will be one upper limit. Upper limit is like mass of entire universe. That is the upper limit. You cannot have a black hole which has more mass than entire universe. So that theoretically we have one upper limit. Lower limit we don't have. Actually, why I'm telling this limit? See the process of formation. You are compressing a star by its own gravity, right? I mean, when a star core is in its last phase, when you are when a star core is compressing due to its own mass, it's not a, I mean, there is no external force involved, right? It's only gravity. But if you have some external trigger or external force which is compressing, which is driving more compression, then you may have, right? You can make even Earth as a black hole. Earth is very less massive than Sun. So you can make Earth as a black hole if you compress it up to a tablespoon size. I mean, few inches. So if you can compress up the Earth mass, so you can imagine like a very kind of daitya, which is compressing. So Earth can become. So you can have, in principle, you can have black holes of even smaller masses.
Yeah, I read somewhere a few months back that there was some black hole which was produced in laboratory.
Actually, I don't really recall the exact news, but I think it was related to one
So
of the LHC discoveries. I mean,
Okay.
Large Hadron
So that
Collider.
means if so you want to say that it's the stars, they, since they are doing it by their own, so if
Mm,
a star has a mass of 2.6 times of sun, then only it can by own become a black hole. Otherwise it
yes,
will become a another species. It will
another
also
species.
die. Yeah, it will also die, it will become a dwarf, but not black hole.
Aaron, there is one more very funny stuff. Like if you have more mass, you are more unstable. So
Yeah,
same
sure.
way, if stars are more massive, they have very short lifespan. So don't be obsessive. Huh? So if it is very, I mean, massive stars have very short lifespan, and very small ones are having very long lifespan. And there are many stars which will even live forever. I mean, you can say live, they will live forever. So
Yeah, in the, so there's a life cycle which depends on mass and radius of stars. Yes. So I think this is like so. Okay, it remains only one question. One part of the question is left. What happens later after the black hole is formed? I mean, is there any other stage of black hole? It will also
actually,
die,
it grows.
or it grows.
It grows
Okay.
in its mass and size. Obviously, mass will increase, and that then its size means size of the
So
event horizon.
by how will it increase mass? It will keep on
See, it's a
dragging. It
feeding.
keep on.
Yeah, it's getting mass from the surrounding, and also one
I
black hole
see.
system interacts with the others, and they kind of eat each other. I mean, they merge and they become another higher mass of the black hole. And even
Okay.
two, I mean, one black hole can merge with neutron star or any massive objects. So this is how supermassive black holes are formed. I mean, if you don't imagine that two black holes are merging or two galaxies are merging, you cannot form a black hole which are having like 10 to the power 8, 10 to the power 7 times the mass of the sun. It's really huge.
Mhm.
Yeah.
So I think this actually answers many of the questions which are related to the black holes different phases of evolution. And now we can move on to another question which has some relation with many of the questions asked there. Why we study black hole? I mean, what's the motivation, since also we are reaching to our 1 hour as initially discussed. So I think now we'll move on to the very crucial questions. So first of all, I would like to just ask about the motivation behind studying the black hole.
Actually, black holes, or the reasons close to black holes, are extreme laboratories to understand many of the processes which are happening in nature. We cannot replicate that in lab. That is one reason why we want to understand, because it's a very strange something which is really, really very exotic is happening by itself. Nobody is doing that, right? So why I'm telling that, I will just give you a glimpse why it's exotic. Because if you imagine, told like black holes are having, I mean, near the event horizon you will have extreme gravity, right? You cannot have that kind of gravity and effect of that kind of gravity on particles motion or plasma or magnetic field or anything. You cannot understand based on laboratories on earth, because you cannot have that kind of gravity. So in reality, if you want to understand the nature of gravity itself in these exotic conditions, or nature of photons, nature of particles, nature of magnetic field, nature of even I mean, very different subatomic particles, you one can theoretically understand, right?
Yeah.
So those laboratories cannot be made on earth. This is why we, very first thing why we study. these black holes. Yes. And they are, and second thing, they are somehow, because black holes are affecting the evolution of universe. I mean, I don't have time to go through all those stories, but thing is, one black hole is interacting with other in the form during the formation of a during the life cycle of a galaxy, and it's affecting its neighborhood. In principle, it's affecting the life of its a single galaxy itself, and one galaxy, two galaxies, and this way galaxies are merging and generating supermassive black holes, and those are having effect on their own behavior and never behavior to the neighborhood. So this
Sure.
means these black holes are affecting the evolution of the universe as itself. So it's inevitable to kind of not study and
Not
understand.
investigate. Sure,
Yeah.
sure. Yeah.
So this is how we are performing different kind of um, tools, but making different kind of progresses in this field.
Yeah,
Yeah.
actually, there is a related question on this. Do the black holes affect the planetary atmosphere? So
Actually,
I think it's very early to say, but yeah, if the effect is there, if being it minuscule, the effect will be right.
as I pointed in my discussion earlier, effect of a black hole at distant, I mean large distances, will be the same as having sun as its normal size, normal life on Earth. The effect of sun on Earth is same. It will be same if even sun has become a black hole, because distance
Yeah,
is
sure.
far.
Yeah,
You will start seeing abnormal effects. It's called I ergosphere or something. You'll see start you will start seeing differences in the nature of gravitational field if you are within that limit. And definitely, if you are within event horizon, you will see entirely different perspective of any event happening in your neighborhood or with you. So basically, no, it is not having any exotic effect on our atmosphere, planetary atmosphere, or planet's life cycle if it is very distant. But if entire solar system is very close to these systems, definitely it will be highly distorted, because as I said, that change in gravitational field with the distances very rapidly, it changes very rapidly. One tip will face very high level of gravitational force in comparison to other. So basically, there will be a gradient in the force in a body, human body. Even if you are close
yeah,
to a black hole,
yeah.
you'll
If
see
we are close
different
to
force on your head
black
and
hole, we will
so.
be, yeah, shredded,
And it's called
shredded in
spaghetti.
pieces.
Yeah, it's called spaghettification. This is very very nice concept. So anything going very close to the event horizon, it will be spaghettified before it.
I see. Yeah, that's a new term. Spaghetti is actually a structure like noodles, where the cross section is smaller compared to length. So
Yes, 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 yes.
wonderful. So
Uh,
since we have actually moved past our time, so I think I should now take everybody, our 48 participants, to the main question. Can you discuss more about the discovery of black
okay.
holes at direct imaging and the magnetic field in the layman's term, in the term which our participants are?
Okay, let me try to emphasize it in my simplest way if I can. So the quest of understanding a black hole and verification of general theory of relativity, or I should say, does black hole really exist in a way how Einstein says, or it is it lies in a very different unknown ways. So Einstein's theory predicts like there will be one event horizon. Okay, event horizon means after that you will not see any photons or mass or energy coming back to you. So that kind of reason will exist, and there are many implications of general theory of relativity. So I will not go to details. Very simple thing: if black holes follow general theory of relativity given by Einstein, they should have one event horizon. Okay, there was a modification by many people. They say that even event horizon is not needed, but that is different story. Okay, so in order to do that, you have to have some way to kind of resolve, I should say, resolve the inner part, because you want to see event horizon which is sitting which is a region around a black hole, and that black hole is sitting inside a galaxy, or say, yeah, it's at the center of some galaxy eating matter. So you have to somehow resolve to very tiny reasons. And resolving means, I should say one simple thing, like resolving means if you can read two alphabets which are very far from you, and you can see that the both two letters are apart, so that is how you resolve. I mean, if it goes very far, you cannot resolve two alphabets. I mean, that's what one face when you go to these aankh wale doctor ke paas. So what happens if you want to resolve, and I would say one term, micro arc second, means like, you can imagine there is a 1 degree angle. Okay, you split 1 degree angle in 60, it will be 1 minute, and one and if you further split those each in 60, it will be 1 second. So you can imagine that very tiny angle, and it will be 1 second, and that should be divided into 10 to the power 6 times. Then you will have micro arc second. So that, I mean, if you want to see something in the sky, you have to resolve this much to see the nearest supermassive black hole, which is sitting at the center of M87. And we were lucky. And okay, before going that, I should say that resolving power depends upon the size of telescope. It's like one parameter. Another parameter is like the wavelength at which you are investigating. So size of the telescope, you cannot, I mean, you are limited by very nice techniques. We ended up having this event horizon telescope concept of having many telescopes coordinating together and observing same object same time. Okay, that is one way you can increase your effective aperture. Second, you should use correct wavelength for your size of the telescope, because, and we were lucky because size of the earth is exactly matching for the 1 millimeter wavelength to resolve that thing. And technique to observe 1 millimeter is really doable now. It's like it has revolutionized this field. So using 1 millimeter wavelength of electromagnetic radiation coming from M87 and using event horizon telescope concept, what happened, it started very, I mean, it
So
started
this
long ago.
M87 is the name of the object, Messier 87.
Yes, Messier
Okay.
87 is the name of object, like that is the
Yeah,
nearest
that's how we
supermassive
identified.
black hole
And
outside
for,
Milky Way.
so in order to resolve the event horizon, which is the the emissions coming from that region, you had to, and the team had to do two very new things. One, to increase the aperture up to the size of Earth. Thankfully, by nature, as you told, we are lucky, so we were meant to discover this. Okay. And so that is one thing. And the second thing was, yeah, okay. And the second thing was you chosen a wavelength which can let us resolve by this huge aperture telescope. So these
Definitely,
are the two.
definitely.
Okay, go on.
Yeah.
Yeah.
And then I mean, it was a challenging, if challenging effort, which Event Horizon Telescope Consortium uh, did very nicely. And this is the image which I am showing. This was the first image created by using Event Horizon Telescope in 2017. And I was lucky because I was part of AstroSat, and I was contacted by the one Event Horizon Telescope core member, Sarah Markov, that can we coordinate using AstroSat and other observatories. So I had a written proposal for New Star to follow some of these EST targets. And this is coming to the M87. This is one, I mean, if you combine the data from EST telescopes, I mean, they have generated this very nice image. And this is like direct image of I mean, these bright. I should talk about these image because this image may be confusing for others, many people. This dark region in the center is the region from where we don't get photons out. And these bright patches are the kind of in the photon orbits from where the photons can escape. Okay, this is why we are having these bright and dark regions. This is, and if you compare with your solar system, entire solar system is inside this white circle in the, I mean, don't, I'm not saying that our solar system at the center of this black hole, but just comparing with the size, this is whole solar system is staying inside. And Voyager is the one spacecraft which was sent long ago to go out of our solar system. So this is where it has reached.
I
So
think
okay,
Voyager is the farthest, I think, from instrument
furthest
which is sent.
man-made satellite.
Yes, furthest sent instrument. Yes. Okay.
Okay. So this is what EST had observed in 2017, but it was published in 2019 because it takes a lot of effort to combine images and do the data analysis. So from 2017 to April 2019, and 10th April it was published. I mean, not published, released. Publication was already accepted before that. And same, this is like using unpolarized light. And if you kind of overplot the polarized one, I mean, use the polarized one, then you get the image what you had shared in the introduction. And basically, this polarization tells a lot about magnetic field, because not every emission process can generate polarized radiation. So for any emission to be polarized, it should belong to certain known emission processes. Okay, so I will not go details. I mean, details are already available, and just want to highlight this is what we know now. So we started observing something which was of the very far scale. Now we have zoomed to the centers, and we have seen, yes, event horizon of a black hole do exist, and we have proof of that. So this is very effective way of verifying existence of black hole.
Wonderful. This sounds chilling, considering now we have the direct images of black hole, and also how the magnetic fields are in their surrounding. This is very nice and very proud moment since India and you are also a part of this kind of discovery. So I think on this big node,
Yeah,
we
I should
can,
say it's the learning
yeah,
phase. I mean, we
yeah,
are,
sure.
because we are witnessing something, and we same time we are also deriving a new methodologies to discover furthermore, and also new challenges. Like we are also discovering something we don't understand. I mean,
Sure, sure.
so this is kind of evolving phase.
So I think this ends our planned discussion of the podcast, but we have a lot of questions. So I think it will be selfish not to take
Yeah, I
them
mean,
which
go
are
ahead.
okay. So I think now up to the point we end, I will try to take the questions which were put on. Some of the questions were already addressed, so I will try to skip them. So guys who have asked questions, if your question is skipped, then probably at some point of the discussion it has already been asked. Okay, so okay, so I would now like to put a question by Akanksha Singh. She said that, as he said, black hole is like a hole in a fabric. Then where are these holes lead to? Wonderful. Is there any theories? What is inside it? So some concise answer from you, Sunil.
Okay, so I mean,
Yeah, where are these holes lead to?
actually,
If these holes are like gravitational field lines which are shooting up, do they have any ending somewhere, or they meet or never meet?
I mean, see, hole in fabric means it is not like it is not like a cloth on which any massive object is put and then cloth is spent. I mean, this is just analogy. Uh,
Okay, how do
okay.
we mute? Sunil, you are muted, so can you unmute yourself and then yeah.
Yes.
Okay, go
Yeah.
ahead.
So it's like kind of hole in the behavior of space and time. It's not like a hole in some physical existence of the universe. It's not like a hole in the existence of the universe. It's a hole in the kind of behavior of space time. There are reasons when time doesn't behave properly. Okay, so behavior of space and time together defines the behavior of any point in the universe. So these singularities are the points in space-time where the space or time doesn't behave normally. So they behave abnormally. Why I'm saying? Because uh, time is nearly infinitesimally slow. I mean, infinitesimally slow means it's slowing. It's very slow and it's like changing very slowly. So this means, I mean, the behavior of time is changed.
Changing there, yeah.
So
So the scale by which you measure the things on earth, on the sun, the scale is variant over there. So I think measuring anything from the scale which changes every minute and every second is very difficult.
yeah, I mean, the one very good analogy is like if you were allowed to see something moving inside event horizon, then what will happen? Time for you is faster than time for the person inside. So time for him is very, very slow.
Yeah,
So what will happen? You will see somebody who has entered event horizon. His motion will be very slow. For you it will be very slow. So somebody has told like it will be so slow that you will be bored to watch and go to home. No, no, we will not watch. He is just standing there. But for him, for the person who is inside, time is really, I mean, he is just moving to the singularity. He is moving to the ending to the singularity pretty fast. So somebody has done said that don't overreact. Don't do anything if your spaceship is stuck in inside the event horizon. Let it move slowly. Anyway, you have to go. It's your ultimate end.
destiny.
Yes.
Okay, wonderful. So it's just that I think so. The next question from I can take, which probably is not taken up yet, is from Sakshi. Sir, what about the entropy inside a black hole? Does it keep on increasing, and can a black hole increase the entropy of universe?
Actually, very nice question. And unfortunately, we could not discuss to the thermal property of,
Actually,
thermodynamical property.
I wanted to go there.
Yeah.
So if you have time and stamina in you, you can put on some words about.
Actually, I will not go very detailed because we are anyway going out of the time schedule. We have
Yeah.
another meeting afterward, but I will share one. Okay, I think it will be difficult to find it here.
Yeah, it will
Mm.
take some time, so we can move
Yeah.
on to other questions. Yes.
Okay. No, no, I will just talk about answer her question.
Okay.
Yes, I mean, we know the disorderness inside a black hole is theoretically very high. So entropy of a black hole is really high. And why we say that, I mean, there was one discovery, I mean, not discovery, I should say the formulation by Stephen Hawking, that, in vacuum, they spontaneously matter and, I mean, matter and antimatter, right? And not antimatter, I heard, should I, particle or antiparticle. Particles and antiparticles are produced in vacuum, out of nothing. In vacuum, out of nothing, particles and antiparticles are produced, and they spontaneously produce and they combine. So what will happen close to I mean, black hole? Suppose a particle is, I mean, this particle antiparticle pair is created, and one pair, before they recombine, one pair is sucked into event horizon. Then obviously other pair, if it is not going inside, it will go out to the universe. So it cannot combine, right? So it is a real particle which is coming out. So
Right.
in principle, overall picture will be like a black hole is creating particles. It's emitting something. Okay. So means black holes are emitting something, and from your experience, if you have a black body, I mean hot body, what it does, it radiates something. Same analogy, if you see, same analogy. Black holes are something which are creating particles, the particles are living out. Okay. So this is one way of understanding, like, okay, this was postulated by Stephen Hawking. It's called Hawking's radiation, which is coming out. So this says that, yes, black holes are also having temperature. Why he said it's temperature? Because if something is hot, then only it can radiate. So using same analogy. So there is a branch of theoreticians. They are studying the entropy of black holes and trying to understand what will be the fate of a theoretical black hole after the, I mean, there is another concept called black hole evaporation. So what will happen after, because if you wait for 10 to the power 68 years, 10 के आगे 1 के आगे 68 शून्य लगाओ, इतने years तक अगर wait करो, तो एक black hole अपने आप evaporate कर जाएगा. And do you know, we cannot. 10 to the power 68 is like, no, it's not possible to wait for that. So theoretically, a black hole will be finished if you follow the evaporation of the black holes. They will die itself. But it's like exotic I mean thoughts, experiments.
It's like a
And
theory which is
it's
difficult
an
to test.
entire
Yeah,
branch is studying entropy of black holes, and then what will happen, the fate
sure.
of a black hole. And there are also questions like, do we have something similar, because this is singularity, and the universe was also formed from a singularity called Big Bang.
Big Bang.
So people also have suggested, like, are are these black holes are also going to end in similar, like universe also started from a singularity, And black holes are like a singularity, and you are keeping you are adding mass to it. At the end, will it end as a singularity again? I mean, like a bang, not big bang, but some bang. So, I mean, people are working on those, and I'm really not expert in that field. Sorry, but this is what I could say.
Yeah, great. So, wow, there are actually a lot of questions. So let me. But while answering these questions, I would urge the audience to keep listening, because while answering the questions, Sunil is also answering some of other questions. So I will not then put on these questions later on. So, okay. So in this list, the next question is from Soumya, and he or she asks, pair production cannot happen in empty space. When there is an accreting disk, pair production can happen, and black hole emit Hawking radiation. But every black hole do not have accretion disk. So in that empty space,
Mhm.
pair production can happen. Does this type
I
of
mean,
black hole also emit Hawking radiation?
okay, good. Actually, when I talked about Hawking's radiation, I never told that there is availability of mass around in this around event horizon. What I told, theoretical black hole, it doesn't have any mass. It doesn't have anything. Just a black hole sitting in vacuum. And it's experimentally proven that spontaneously formed pairs from vacuum itself, like particle and antiparticles, they are from spontaneously, and they are combining again and becoming I mean, vanishing. I shouldn't say making vacuum, but it's like vacuum is also not a vacuum, I should say, if you introduce time dependent phenomena to it. Okay, so no, in principle, you can have pair production. This is not a gamma gamma pair production. This is not a gamma gamma pair production or electron positron pair production. This is like particle antiparticles are producing in spontaneously out of vacuum. And accretion disk is something different. Accretion disk is I mean, it's then, and also I should say that Hawking's radiation doesn't come in any detectable frequency or an wavelength range. So it's
Yeah.
like a theoretical radiation, a radiation which cannot be verified even in future. I mean, I don't know, maybe some
It's a
technological
logical,
revolution.
yeah. So it's a logical analogy, because the radiation also contains the information. So yeah, this also
Yeah,
this leads to all the thermodynamics occurring
yeah. So
inside
I
or in
mean,
the exterior.
since he mentioned about accretion disk, so I should say that the black holes which are lucky enough to have enough matter in the surrounding, so that they can attract it, the matter can fall onto it, and black holes can grow. And actually, what happens? Matter cannot directly fall any object, because matter is also having some kind of angular momentum, and this object is also having a spin. So effectively, it has to pass through a disk, and this is what is called accretion disk. So the radiation from the accretion disk is not by pair production process I talked earlier. These processes are like bremsstrahlung. You have a charge moving in a high in the presence of electric field, it will lose energy. It is like there is a magnetic field and a charge is moving, there will be a synchrotron radiation. And since accretion disk is hot enough, because it is interacting, matter is interacting with it's a neighboring material, high dense material, so there will be a friction, and due to that friction the disk is very hot. So if it is very hot, then you will have black body radiation. So whatever radiation we are getting out of gravitating, it's called gravitating black hole, means it is accreting matter. Accreting black hole is dominant by these processes like photoelectric, or I should say, I mean, all these known radiative
Known
processes
radiations,
are
yeah.
happening. Yeah, it's
Actually,
not.
yeah, you are going getting into the question by two of other participants, one Akhila and one Lohi Srivastav. They asked that is a black hole a perfect black body, or black hole is just like a black body? Is it true? So I think you can continue.
Actually, what observationally we study, I'm talking about that. The black holes which are detected through its effect in the neighborhood, I mean, due to its glow of accretion disk or due to its jet, multiple radiative processes are taking place. The disk is pure black body radiation, okay? But there, due to presence of magnetic field and channeling of material in the form of jet, the black holes do have highly collimated radiation due to the particles which are moving in a magnetic field with the relativistic velocities. One means the particles are coming out of the disk atmosphere or disk. They are coming out and thrown very rapidly to the axis perpendicular to the disk, and those particles are emitting due to synchrotron emission. So if some of them are not relativistic, they are slow, then you will have cyclotron emission. You can imagine, like, there are charges, and a charge is moving, it will lose energy and it will produce bremsstrahlung. Sometimes other variants of bremsstrahlung, it may be because your source is moving relativistically or not. I mean, there are a number of processes happening there. But for perfect theoretical black hole, when we are talking about, it's a kind of composing entropy in, I mean, high order of randomness inside, and you are seeing this Hawking radiation. uh, I mean, this property is perfectly derived by thermodynamical formulations. But yes, I really don't know whether we can kind of compare to a perfect black body system or some deviation of from that. Yeah, not to my understanding. Yeah.
Okay, so I think we are getting to an end. Wow. In the questions, I think there were like 50 questions. So wonderful. This is kind of, yeah, achievement. So I would just only take this final question, and if you feel free, feel comfortable in answering, if ultralight axions are present at the vicinity of a black hole, then are they considered the source of orbit alignment of nearby stars?
Wow. Well, I mean, I should say that it's
That's,
really beyond my reach.
yeah,
But
that's
yes,
the reason I
yeah,
asked. Yeah. Okay, go ahead.
yeah. But I should comment, like, the concept of axions, if I understand, these are the particles, exotic particles, which are known to be moving with the velocity. I mean, they are postulated to be the particles which can violate this special this limit, speed limit of the light. But yes, I mean, there are even, I mean, using same collaboration. See, my collaboration, this HES collaboration, which I am part of, is also dedicating is study in different fields. So discovery of axion particle or investigation of axions using TeV astronomy instruments is also one of the very exotic field of research. But I really am not uh, expert in that. Sorry. Yeah.
So yeah, that's thank you, Sunil, for taking up these many questions, and I think I have come to an end in terms of taking up the questions, as well as the questions I thought of putting up in the light, so that the discovery of this black hole and what are the black holes, what is the life journey of a black hole, and how this connects us with our everyday school textbooks. So I hope some of these points have been considered in this discussion, or mainly the discussion by Sunil. So with this, I think from my side, I would like to thank all of the participants, Sunil and the moderators for taking care of smoothly running this session. And if Sunil, if you have to say anything, you can please go ahead.
Yeah, really, thanks a lot, Arun, to have this kind of session. But I should say one disclaimer. I mean, it is really very hot field of the research, and there are plenty of material available on YouTube and other, many websites and many research papers for the public use. So I would really want to say that please go through those videos and use your time to understand more about this system. What I wanted to say, that since our program is not to show slides, not to show blackboard whiteboard stuff, just to discuss about things, so it's really very difficult to talk about black holes without having any slides and all. It's really very difficult, and I think I have done some sort of justice, but not properly. So I would want to say one more thing, that maybe in future we will invite somebody, just like a lecture, not like discussion session this way, like a proper lecture on a black hole and related to one focused aspect. We will plan accordingly,
I
and we'll
think
let
the
these people know.
the idea, the motivation behind this Ask Us podcast, where the discussion is the top priority, is to inspire questions and
Yeah,
just
definitely.
put the idea, put the seed of what's going on in certain experts field of research. So I think this particular session justifies it. So but again, in order to be complete justice, if your questions have not been answered in the discussion session, you are most welcome to put the questions to Sunil and to us, and we will try to find out the relevant documents and send it to you according to your level of understanding, in terms of either you are from up to 10th or 12th, or you are in graduation. We'll try to send the documents accordingly.
Okay,
So
just want to do one thing. I mean, that's what we were doing in last sessions as well. We should open for 5 minutes to anybody who want to interact and use their own mic. Yes, and
okay,
it's open
perfect.
for everyone.
Yeah,
But one by one, use your raise hand
yeah, so you
option.
can, okay, you can raise hands, and I will then ask by names, and you can unmute yourself and ask questions. Please go ahead if anybody has questions or comments, or as an audience, if you have
Yeah,
some
and
feedback.
suggestion maybe.
Yeah,
Suggestions. If not, this means we have made a lot
yeah, I
of.
think no, I think this is a long session, because the session starts from 1:45 or even before that, so it's already approximately 2 hours. So I think it's
Okay.
time that we yeah, it's time that
Okay. Then we
can,
can end this session. Yeah.
if
Actually, before ending, I just have two comments to make to the audience. So, one is a request to join the United Science Foundation social media platforms. Please do join all the platforms, and for latest information about future events and all the activities conducted by USF, you are requested to join our Telegram channel, and also please follow us on all the other social media sites. And another aspect is that so in our poster we had advertised a point regarding career in astronomy and astrophysics. So maybe in later Ask Us session, or maybe in some other event, we will cover that point. So we request you all to keep in touch with United Science Foundation's activities. Yeah, thank you.
thanks, Dipti. So this kind of from officially ends the broadcast broadcast from our side. Looking forward to your active participation, just like this very active participation, the next time we meet. Till then, take care, be safe, and take care of your